Okay, good afternoon, everyone. Welcome to a very special IOA Colloquium today. It's a great pleasure for me and also honor to introduce Professor Andrea Ferrara, who is visiting us for the last few weeks as part of the IOA Distinguished Visitor Program. Andrea is a professor at the Scuola Normale Superiore for Cosmology, and he has been there also being the Dean for Sciences and part of the Prorector for Education and Internationalization. We know him, of course, very well. He has a very distinguished career. He has contributed very importantly to our understanding of the early universe, in particular for the formation of the very first stars and galaxies, the formation of black holes, and then also how these stars and black holes reionized the universe. He has held a wide range of different, very distinguished appointments, including the Blau Professorship at Groningen and the Beatrice Tinsley Visiting Professorship at the University of Texas at Austin. And he has received a long list of prizes. I'm mentioning just two of them here, the Humboldt Research Award and the Severo Ochoa Prize from the IAC. Beyond his scientific achievements, Andrea has played very important roles, leadership roles in the scientific community. For example, as chair of the SKA Science Engineering Advisory Committee and as contributor to both the Euclid and JWST missions. Andrea's influence has been far-reaching. In particular, he has mentored more than 50 students and postdocs, many of whom are now leaders in the respected subfields, and he remains very deeply passionate for teaching, as I have met him actually many of the summer schools over the last 2-3 years. Beyond astrophysics, Andrea is actually an electronic music composer under the name of Angoa Kwao, which is, I think, a lovely reminder that creativity comes in many different forms. So if you sense a certain rhythm in his talk that is going beyond just the bursts of star formation, it might be because of his musical background. So in recent years, I think the discoveries from the James Webb Space Telescope have clearly re-energized Andrea, and it's been a joy to see him as excited as ever about these early discoveries from the James Webb Space Telescopes. And so we are, I think, all very fortunate today to have him here to talk to us about the beautiful confusion, super early galaxies seen by JWST. So please help me in joining, welcoming Professor Andrea Ferrara. Yes, welcome.
Well, thank you very much, Sandro. What can I say? Thank you and good evening, everyone. It's a real privilege and an honor for me to deliver this distinguished lecture today. And I would like to thank the IOA directors, Professor Cathy Clark and Professor Mark Wyatt, for giving me this unique opportunity. I'd also like to thank you all, actually, for the exquisite hospitality and the scientific discussions during these intense 6 weeks that I've spent here in Cambridge. So I will discuss some recent advances produced by the James Webb Space Telescope, or JWST in short, with the discovery of galaxies at redshift larger than 10 that I will define, at least for this talk, as super early galaxies. So these galaxies are at the frontier of the known cosmos. And so the first question is, what do we expect to see? To answer this question, we have to remind us that our basic knowledge of this type of topics comes from the lambda CDM cosmology combined with galaxy formation theories. So these are embedded into high-resolution numerical simulations like the one that you're seeing now, showing the interaction and the growth of a group of galaxies at redshift around 10. So galaxies, as you see, grow through mergers and Fourier's matter accretion funneled by filaments and the cosmic web. Interestingly, we see that some small intermittent disk structures are already in place at these very early epochs, and these are less than 500 million years from the Big Bang. So now, and for the first time, we have the chance to directly compare this synthetic universe with observations. So what are the observations telling us then? So the situation, as I mentioned before, changed dramatically with the appearance of the JW. And in fact, only 3 years ago, in November 2022, the situation of the known galaxy was as represented in this plot, showing the absolute magnitude of a galaxy with respect to its redshift. As I said, today we will be mostly concentrating on galaxies that are redshift larger than 10. And so one of the very first papers that appeared by Naidu et al. November 2022 was reporting these 3 galaxies with these names that will come back over and over in my talk. And so these 3 galaxies were the ones that were were discovered at the time with photometric precision. So today, 3 years later, that graph has changed like this. So now, again, we are showing absolute magnitude versus redshift, and you see that there are here these red dots that are galaxies that are spectroscopically confirmed. So it's quite a giant leap with respect to what we had just 3 years ago. So now we have 40 confirmed sources at redshift larger than 10. For me, it's almost a dream that I could give an entire talk on galaxies at redshift larger than 10. This is something that I would never dream of in my career. Now, the most distant galaxy is called MOM Z14, and that's just slightly above a galaxy that has been discovered here in Cambridge, GSZ14, but they are both at redshift more or less 14. And there is one galaxy that was among the first to be discovered, GNZ11, that is at redshift 10.6 and is the brightest one with an outstanding magnitude almost minus 22 that is in the circle. Now, this is kind of a superstar galaxy, and it's interesting to go back to a little bit of history here. Not long history, but some history. So GNZ11 was the presence of GNZ11 and its being at the redshift larger than 10 was already more or less suggested about 10 years ago, when HST took as little as Grissom spectrum of the galaxy that you see there in blue. So you see that this is a very noisy spectrum, but that fact did not prevent these colleagues to being able to assess that there was indeed a high redshift galaxy located a redshift larger than 10. Now, the same galaxy, the same spectrum seen by JWST, it's this one. So immediately you see the difference and why JWST is so important for our progress in the field. So not only the quality of the spectrum is incredibly better, but it's also more extended in wavelength, extending beyond 5 microns in observed frame. So with this redshift, we were able to observe many emission lines that help us fixing the redshift to a very solid 10.6, which is not too far from the original one. So, but it's impressive to see how the improvement went rapidly through in these 3 years. Now, immediately after the first galaxy were discovered, the first super early galaxy were discovered 3 years ago, people realized that we have a problem. So what is the problem? So this is a graph again from 3 years ago. So you see that there are the 2 galaxies that I showed you before, the very first detections. And from these 2 galaxies, it was possible to determine a kind of rough luminosity function that is the number of galaxies per unit UV magnitude. And so you see that the straight line exceeds very much the other lines that are models, pre-JWST models, so the lines that you see down here are models prediction that were predating JWST. Now, there is a data model tension, which is obvious. But of course, at that time, we only had 2 galaxies, so people were not really making a big deal of this tension. Unfortunately, or fortunately, I don't know, when the new data came and we have now a much better, very solid determination of the UV luminosity function, you see that this tension has been confirmed now on a much more solid ground. And again, the data are pretty much exceeding the pre-JWST theory, particularly in this region where the galaxies are bright. That is called the bright end of the luminosity function. So now, this is only one part of the problem. And so let me step back 1 second and try to go to give you an overview of the JWST discovery that is bringing problems that we are trying to solve here. So I already told you that the JWST discovery are showing that there is an unexpectedly overly large number of luminous galaxies at redshift larger than 10. And this is the graph that I showed you before. But also, these galaxies tend to be massive. That means that their masses, stellar masses, are of the order of 10 to the 9 solar masses, which is not large in absolute terms, but it's certainly very large for being a redshift larger than 10, because this type of objects typically represent 3 or 4 sigma peaks of the density field in the unit, or the cosmic density field. In addition, they have blue colors. This is also quite difficult to understand or unexpected, because we are used that in the more local universe, the more massive galaxies are also the ones that tend to be redder. Instead, these are very blue. And so for these reasons, we call them blue monsters, to say that they are massive, blue, and luminous. The same issue is concerning the attenuation by dust. They are blue because they have little dust attenuation with typical AV values, attenuation in the visible less than 0.1, which is essentially very, very small. And finally, they are super compact. So these galaxies have sizes that are only slightly larger than present-day molecular clouds, 100 parsecs. So one of the examples, just to give you a visual perception of the thing, is the galaxy GIZ2 at redshift 12.34. And you see these are the post-stamps. You see that the galaxy is very compact, barely resolved, or even perhaps not resolved. And this is located at redshift 12.34. So there's been a lot of work on these galaxies, as you see from the list here. That is also partial, but now we have a very good knowledge of the census of these galaxies. So having these problems stimulated us to think as theorists, how do we understand this situation? So we went back to the simulation that I showed you at the very beginning, and so the idea was just to try to see galaxies at redshift larger than 10 in the simulation and check whether there were any they were similar to the ones that we are observing. So we went back to our simulations, the Serra simulations, and which are zoom-in simulation with high resolution, spatial resolution of about 10 parsecs. So we can resolve even galaxies that are 100 parsecs on a size, in radius. And we found one digital twin of these galaxies. So we call it Amaryllis. And the appearance of Amaryllis from redshift 14, 11.5, 10.6, and 7 is shown by this set of maps. Now, you see that the galaxy clearly grows. There are satellites, merger events, And finally, also develops a disk. And so if you look at the evolution of the stellar mass as a function of time, or redshift if you prefer, for this galaxy, you get the white line that you see in the left panel here. So this is compared to the galaxy, or at least the most prominent galaxies at redshift larger than 10. So you see that it's pretty consistent with the values that we measure. And then it nicely merges, the history of the galaxy merges with the galaxies at redshift 7 that we have studied with ALMA. These are called the Rebels galaxies. And so probably the most massive galaxies could be linked to the most distant galaxies at redshift 14. And the star formation rate that we derive, it's increasing, it's flickering, particularly due to merger events. And quite nicely, or even surprising, at least to me, is the fact that these galaxies at redshift 7 indeed shows the presence of a disk that is also observed in the Rebels galaxies. These disks are large and relatively cold. So this is something that give us some confidence that we are doing something which is similar to what we are observing. And so to allow a more detailed comparison, what we have done is just to put together in a single table the properties of the synthetic galaxy, Amaryllis, that you see in this column, versus what was at that time the most distant galaxy, GSZ 14, redshift 14. So you see that from the number of green checks here, that the stellar mass, the gas mass, the gas fraction, metallicity, star formation rate, age, number density, ionization parameter, they all seem to be more or less okay. But there's one thing that just made us unhappy, the fact that we are overestimating the dust mass by about a factor of 10. So everything is okay. The galaxy looks like the one we observed, but the dust mass is large. And so the implication of that comes out immediately when you look at other quantities that are affected by the presence of dust. In particular, we find that this galaxy is 2 magnitudes fainter than what we observe. It has a UV light radius which is smaller than what we observe, and it has an AV which is 10 times larger than what we observe. So that was really very puzzling because the simulation overestimates the dust mass, and this has this effect on these observable quantities. So although the simulation includes both on-the-fly radiative transfer and supernova feedback, the galaxy is still obscured. And so, indeed, we find that AV, as I was saying, is 3.3, which is not what we observed. So we scratch our heads and said, why is that? And my favorite explanation, or at least what we think we have understood, is that the supernova explosion energy in these galaxies is radiated away quite efficiently due to the fact that the densities are very high, of the order on average of 1,000 particles per cc. And therefore, the outflows that were supposed to remove some of this dust are almost suppressed. So, but the outflow should be there. These are all treated self-consistently. So are we missing some physical ingredient? To answer this question, let me step back again and go to some more general overview of the problem. So first of all, we want to remember that we want to have galaxies that have to be brighter because the ones that we observe are bright. And so in order to increase the UV luminosity of a galaxy, you have 3 knobs that you can use. The first is the star formation rate. The second is called K1500, which is the conversion of baryons that you put into stars into UV photons. And finally, e to the minus tau, which is the absorption by dust, which is also affecting the UV luminosity. So the first idea is that you can crank up the star formation rate. And you can do it in 2 ways, essentially. One is to increase the star formation efficiency, that is the conversion of gas into stars. Or you can also think that the star formation rate grows because there are stochastic events when the star formation rate becomes large. Alternatively, you can try to increase the UV production efficiency by, for example, adding population tree stars or top-heavy IMF. In other words, you are trying to get more UV photons per baryon that you put into stars. Finally, the third alternative is that to reduce dust attenuation. So if you reduce the absorption, the galaxy will become brighter. So I will not discuss too much, actually at all, about this possibility. And the reason for this is that there are three reasons for which I don't consider the playing around with the UV production efficiency is working. Because first of all, POP3 stars are excluded in this galaxy because we can measure their, we do see emission lines, we can measure more or less the metallicity, and they all turn out to be around 10% solar. So this is not where you expect to have population tree stars. The same can be said for top-heavy IMF, where in order to have a top-heavy IMF, you need to have low metallicity, at least according to some theories. Finally, we have to remind that if you use the top-heavy IMF, it's true that you increase the value of K1500, but at the same time, due to the increased feedback, you decrease the star formation rate. So the product of star formation rate times kappa remains more or less constant, so you don't gain much. So I will not consider this hypothesis. This is a personal choice, and also for reason of time. I would like to discuss more, but for reason of time, then I will consider instead the third possibility. So my plan for the next 3 slides is just to discuss these 3 processes in a sequence. So we start from the star formation efficiency, stochastic star formation, and reduce dust attenuation. So increase the star formation efficiency is certainly a viable solution. This can be done by saying that you may have what are now called or known as feedback-free bursts. What are they? So these are bursts of star formation rate in which you convert a very large fraction of the baryons, 80% up to 100%, into stars. So these large conversion efficiencies require a simple condition. So you want to form as many stars as you can before the first supernovae start to explode. So there is a delay time from the formation of the first stars to the time at which the first supernova blows off and possibly disrupts the star formation activity. So that takes usually 3 to 5 million years. So the time scale on which you form stars, on the other hand, is the free fall time, which is proportional to 1 of the square root of the density. So it turns out that in order to have a large conversion efficiency, you need to have a large density, or larger than at least 1,000 particles per cc, which we have seen that at high redshift maybe is not crazy, okay? However, if you present this picture to people that are working in star formation and molecular clouds, they think it's a little bit odd, because what happens is that even before the first supernova explode, you have a number of things that are going on in the cloud. First of all, you have stellar winds. Stars produce winds. They produce H2 regions where the ionized gas pressure is very high. There is radiation pressure both on dust and also via the Lyman alpha line radiation pressure. So let me call these processes in a word like pre-supernova feedback, okay? So this pre-supernova feedback can limit very much the efficiency. So basically you don't get to 80% or 100% or even less. And so you can check this in order to test this idea or to prove that this is a correct interpretation. We have been doing several studies, and in particular, this is one example of the 3D radiation aerodynamic numerical simulation of a giant molecular clouds, where you resolve star by star. Okay, and you have radiative transfer, you have H2 regions, you have molecular hydrogen formation, and all the physics that we think is important. But what happens is the following, though. As soon as you form a star, it produces a region where the gas is low density or ionized. And that means that this is effectively a negative feedback, because stars cannot form within these cavities, because the conditions are not conducive to star formation. On the other hand, it's also true that when these bubbles created by individual stars collide, you have compression regions where the density can become high and positive feedback can develop. So there you can form new stars. So there's both negative and positive feedback, up to the point in which the star, the cloud is destroyed by the fact that the energy input is too large for the cloud to survive. So if you, in addition to these processes, you consider just one, that is the Lyman alpha radiation pressure, then you can compute what is the conversion factor of gas into stars as a function of the gas surface density of the molecular cloud, sigma g. I recall you that the region populated by Milky Way giant molecular clouds is this cyan rectangle. And so as a function of sigma g, we see that depending on the fact that you are considering or not the negative feedback and the positive feedback that I told you before, then there are different cases, but and also there's some dependence on the metallicity. But the bottom line is that basically, even in the most optimistic case, you can never go above 30%, and also only in the most massive clouds that are much more massive than the one in the Milky Way. So these are lower limits, these are upper limits to the efficiency, because we are only considering Lyman alpha radiation pressure, we are not considering the effect of the H2 region of the stellar wind. So these are strictly upper limits. And so the conclusion is that this pre-supernova feedback essentially erases the feedback-free burst phase. Now, the second point that I promised to discuss is this, right? Stochastic star formation. So is stochastic star formation able to produce this flattening of the bright end of the luminosity function that we see in observations? Well, in principle, yes, because what happens is that if you, this is a kind of an Eddington bias effect in which you upgrade low mass galaxies that are bursting into a luminous part of the luminosity function. So in order to do this, you need very consistent fluctuations of the star formation rate and therefore of the UV luminosity. These are quantified by the RMS of the fluctuation that I call sigma UV here. So if the fluctuations are large enough, for example, sigma UV equal 2, then you can go from the no stochasticity or no burst case into the red one, which is consistent with the data. So all nice. So again, is this possible? This is in theory, it's possible, but does it happen? So we went back to the simulations and looked for the stochasticity of 243 galaxies at redshift 7.7. And so as an example, I'm showing you one of those. So this is the star formation rate as a function of time or redshift of one of the galaxies that we are considering as an example. And so when you remove the rising or continuous, the DC mode, and you're left only with fluctuation, you find that the sigma, the RMS of the star formation rate fluctuation is 0.19 for this galaxy, but which has a stellar mass of 10 to the 10. We can look at all the galaxies, and more or less we don't see much dependence on the stellar mass here or this fluctuation. and the sigma on average that we find is 0.24. When you transform this fluctuation in star formation rate into a fluctuation in the UV luminosity because of the magnitude system, you get a 2.5 here. And so if you multiply 0.24 by 2.5, you get 0.61. With 0.61, the curve that you would get is this one. So far down with respect to the data. So that means that stochastic star formation variation cannot provide the observed luminosity function boost. But the situation is even worse because the stochasticity is limited also by another constraint, which I think is very interesting, that is related to the metallicity of the galaxies. Because in short, high stochasticity leads to what we call the chemical chaos, and I'll explain what I mean by that. So if you look at the metallicity versus stellar mass relation, and you assume RMS of the star formation rate fluctuation of 0.5, then all the models that you get lie in this yellowish region, so they are dispersed more or less everywhere, while the data, as you see, are consistently around with relatively small scatter around the yellow line. It is only when you decrease the RMS of the star formation rate or the fluctuations to a much modest level of 0.15 that finally you get agreement with the data, and the scatter seems to be the one that we observe. So in other words, if you allow too much stochasticity, the metallicity would also be very dispersed, and so you break the mass metallicity relation that we observe. And so the scatter in the mass metallicity relation implies a stochasticity level which is about 5 times smaller than required by the luminosity function, or to fit the luminosity function. So now, given that these two things have problems, we are left with a third possibility that we want to reduce a dust attenuation. So now, super early galaxy, first of all, we have to note, we go back to the data. And so super early galaxies are very blue. I told you already from the beginning. And now this has been determined with very high precision and by different groups. So you see that this is a graph showing the slope of the UV part of the spectrum of these galaxies as a function of redshift. And you see that there is a trend of decreasing beta with redshift. So as you go to higher redshift, galaxies become bluer and bluer. Now, this is one example, but we have many of those, and they're all finding essentially the same thing. So galaxies are becoming bluer and bluer. So it means that these super early galaxies are relatively attenuation-free. And so what is their attenuation level? I usually don't show tables in my talks, but this one, it's interesting, and I only want you to concentrate on 2 columns. These are 20, because the paper is 1 year old. 1 year ago, we had 20 galaxies at redshift larger than 10. And you see that the value of, in this column, I'm showing the value of the AV attenuation. You see that this all very small. So they are all around 0.1 or even below, with some galaxy having just an upper limit of 0.01. So they're ridiculously small. So that type of data translates into a dust to stellar mass ratio, which is shown in the yellow column. So again, the dust to stellar mass ratio is very small, so incredibly small. I mean, it's very hard for me to believe that these are the numbers, but these are the numbers. So -5, -6, -4. So that means that these galaxies are special with respect to the one that we know. So the very low inferred dust to stellar ratio raise the question of whether in this system dust produced by the stars that we observe has been destroyed. So maybe the stars are there, we expect them to produce dust, the dust is not there, so has the dust been destroyed? The next question, the next plot answers this question. So this figure shows the dust to stellar mass ratio from the previous table for the known super early galaxies. These are the white diamonds that you see here at the bottom. Okay, so these are the dust to stellar ratio. So the violin plot points are the prediction of a dust evolution model, including dust destruction in supernova, interstellar, and reverse shocks. So all the shocks that you can think are there. And there is no account for dust growth, which would make the dust to stellar ratio even higher. Okay, so it's a conservative choice. So there is no account also for possible ejection of dust by outflows. So the predictions, as you see, largely exceed by almost 3x the data. Yet, this model is consistent with Rebel's Galaxies data at redshift 7, which is the horizontal blue stripe. So the conclusion is that dust destruction cannot explain the extremely low dust to stellar mass ratio observed in super early galaxies. So you can ask me, but then why are they attenuation free? Okay, let's make a simple sketch here. So there's some things that we agree. So that dust is produced by stars. And so if the stars are contained within an effective radius RE, the dust should be initially at least co-spatial with the dust out of which it has been produced. So if this is the case, because of the compact nature of these stars, of these galaxies, then the AV that you would measure in such a system is very large. And in fact, we have some examples of galaxies, but they are accumulating. They show very red spectra, even if they are at redshift larger than 10. There are few, and they are to be confirmed, but they are there. 3 days ago, another paper claiming that there are 2 galaxies of redshift 12 that are very obscured, appeared. We need to confirm it with spectra, but there are hints, and this is, we think, what's happening. Now, if instead you allow some mechanism, an outflow, and in particular radiation-driven outflow, because we have seen that supernovae are not efficient in producing outflows in these early galaxies, and so you enlarge your distribution of the dust from RE to RD, which is larger than RE, then remember that the optical depth decreases like 1 over R squared. So you gain a lot in terms of transparency of the galaxy. And so then you would find that the galaxy becomes transparent, and it may resemble what, for example, we see in JWST, that is a galaxy essentially with no dust, or with no attenuation, with very low attenuation. So the answer, if you ask me, why are they attenuation free? The answer is this one. Because their outflow displays the dust to larger radii. Now, why then, you can ask me, why do you think there are radiation-driven outflows? And so let me convince you, give you some arguments why I think that this is the case. So we have to go back to our first astrophysical classes, and remember that the classical Eddington luminosity is given by this expression, and is linearly proportional to the stellar mass. And in the denominator, it has this cross-section, which is the Thomson cross-section, because classical Eddington luminosity acts on electrons, on free electrons. But if you have an Eddington, or a gas with some dust, then the situation changes, as has been pointed out in many papers by Andy Fabian and collaborators. So what you do is just you substitute a sigma t here with the cross-section of the dust, which is A times larger, where A could be up to 500 or 600 times larger than the Thomson cross-section. So that means that your Eddington luminosity, the effective Eddington luminosity, is decreased by 1 over A, with A 500. That means that you're decreasing the effective Eddington luminosity. Therefore, for a galaxy of a given luminosity L, it will be easier to be super Eddington than before, when the Eddington luminosity was up here. Now, one thing that is important is that the super Eddington condition implies that the Eddington parameter has to be larger than 1, where the Eddington parameter is defined as the ratio of the luminosity of the galaxy divided by the Eddington luminosity. But it's simple to realize that the luminosity is proportional to the star formation rate of a galaxy, and LE, we have seen, is proportional to the stellar mass. So that means that lambda E is essentially proportional to the specific star formation rate of the galaxy. Now, given the fact that these galaxies, I told you and I show you, that are very compact and they have a very large UV luminosity, then for them it's very easy to become super Eddington and launch powerful radiation-driven outflows. The condition for super Eddington, that is Eddington parameter larger than 1, it's essentially, you can translate it in a condition on the specific star formation rate that has to be larger than 25 inverse gigayears. So galaxies that have this specific star formation rate that is enhanced or high, they will have, almost by construction, an outflow, a radiation-driven outflow, because they tend to be super Eddington. So with these simple concepts, I try to put them all together in what I call the attenuation-free model. That it's possibly the simplest model that can explain a number of things that I'll tell you in a second. But it has no need for high star formation efficiency or stochasticity or top-heavy IMF. You just need to clear a little bit the galaxy with this outflow, which is a natural consequence of the fact that they tend to be super Eddington, because as you go to high redshift, on average, the specific star formation rate of galaxy grows, okay? So this is almost natural. So this model has some good things, and for example, it explains quite well the luminosity functions of redshift 11, redshift 12. So now, in this way, we are curing this initial tension that we had, and then we can also fit the cosmic star formation rate density. So you see the yellow curve goes through the points, while the other models here are with pre-JWST models. There are also two galaxies to be confirmed here, well, actually a group of galaxies to be confirmed, which would not be consistent with the model if they are confirmed, but let's see. And finally, you can also look at the galaxy number counts. The cyan area here comes from data from the epochs sample. We are going through the data, and by chance, the model also predicts two galaxies at redshift 14. So please don't find more galaxies at redshift 14. So now, is this enough? No. Are you satisfied? No, because I want a more stringent test, because I think that these partial successes are something that models in principle can achieve, but they're not stringent enough, because reproducing a luminosity function or the mass function, it's okay, but it's a prerequisite for me for a model to be really convincing. And so as an example, I think that a more stringent test is represented by star formation histories of super early galaxies, and this is the case of that I'm applying to JADE's Z14. So I'm trying from the model to reconstruct the star formation history. Now, this is a busy plot, but don't get afraid. I will go through it. So this is a log of some quantity as a function of look back time. So the galaxy is located here, and this is redshift 14, and then you go back in redshift. The most important curve is the blue one. So this is the star formation rate of the galaxy. So the galaxy started to form stars at redshift about 26 when it became possible for the galaxy to form stars. And as soon as it starts to form stars, then what happens is that the UV radiation field, and in particular the Lyman-Werner radiation field in the galaxy, started to destroy molecular hydrogen. So the galaxy went through a phase in which it was impossible to form stars, and it was quenched. So there was a pause here, and then as the Lyman-Werner flux was decreasing because the stars are aging, the star formation rate started again. And in the meantime, the dust, this is the dust-to-gas ratio, was continuing to accumulate. Second attempt failed again. At the third time, what happens is that the galaxy started to produce, was large enough that it could produce stars without any break. And however, accumulating this dust that was produced by stars make the galaxy rapidly obscured. So we enter in an obscure phase that you see sketched here, up to the point in which it became super Eddington. And then you have an outflow, and then this outflow depresses the star formation rate, ejects the dust and a little bit of the metals. At the end of the day, when you go and compare the galaxy to the data that we observe, there is a very nice agreement. So we get the UV slope, the MUV, the radius, star formation rate, everything seems to be in place. So we are very happy with this. It's also interesting that in the course of the evolution, at some point the galaxy was bright enough, but not, it didn't produce yet enough dust to be obscured. And so perhaps it had magnitudes that are potentially observable even at redshift 20 and above. And maybe we have already some indication of that. So with this star formation history, what I did is just to produce a spectrum obtained by feeding the star formation rate the star formation history that I showed you in the previous slide into an SED filter. In this case it was bagpipes. And so when I applied the model to GSZ14, I only had the information on redshift, UV magnitude, and stellar mass of the galaxy that were provided by my colleague Stefano Carniani in Pisa. He was so kind to refuse to show me the observed spectrum before I had produced my predicted one. So when I walk into his office with this figure and we compare it with the actual spectrum, which is this one, we were both very, very impressed because, in fact, the prediction was that there will essentially be no lines apart from this carbon-3, and indeed, carbon-3 is the only one, the only line that has been detected. Now we have even better data. But it seems that this could be a test that I consider, at least for myself, very convincing that we are on the right track. Of course, we have other predictions, MIRI spectra, if they will be available at some point for this galaxy. These are predictions that we need to test with the MIRI data. So finally, the later evolution, so we have seen that this phase of the blue monster can perhaps repeat itself, and with some periods in which the galaxy remains after the outflow in a quiescent or in a lull phase, even though cosmological accretion that is very high at this redshift is replenishing the galaxy and perhaps driving into a second cycle. Now, this is admittedly very speculative, and we don't know the duration of the cycle. We need to do better studies on that. But it's tantalizing to see that at least there are objects like that follow this track. And one example of the that I consider a textbook case for the attenuation-free model is the galaxy discovered by Baker and collaborators at redshift 8.5, which shows a very featureless spectrum, and at the same time, it has a very rapid drop in the star formation rate in the last 10 to 20 million years. So why I think this is a textbook case? Because first of all, it's the evidence is the beta is very blue, so it's very blue galaxy, so that means that there's little or no dust attenuation. There are no ionization lines, which means there is a poor starburst as we expected for these galaxies like JWST 14. It shows an extended oxygen 2 line that may indicate that there are weakly ionized gas that has been displaced by the outflow that has cleared also the dust. And it is mini quenched, so it's been, the star formation has been abruptly, and this is important, abruptly stopped by some process which could be the radiation-driven outflows that I've been talking about. And it's a little bit more difficult to do with supernova feedback because energy by supernova is delivered little by little on a longer time scale. But these are things that we need to study. I conclude by saying that so this galaxy could be a blue monster that has been cleared of the dust and has had this star formation rate quenched via radiation-driven outflow. So this is my compressed summary in which I would say that the attenuation-free model explains the property of super early galaxies via the existence of radiation-driven outflows that are almost unavoidable at high redshift due to this high specific star formation rate of these galaxies. So the outflows clear the dust from early massive galaxies, making them blue and abundant. In the history, the star formation history, in my view, represents a very stringent test of these early super galaxies. There are many implications of this scenario. They go from the mini quenching that I just discussed, but also on the possibility that this galaxy contributes significantly to ionization via Lyman continuum escape, and also Lyman alpha. They could also be Lyman alpha emitters, and they might help explaining some peculiar abundance ratio that we are observing. Thank you very much.